How do we calculate the atomic mass? Okay. So, fortunately, that's done for us, but we still need to know how to do it, yeah? Okay. So let's do one of the examples that was on the worksheet. You had two examples, right? Did everybody get one of those? Everybody need one? There you go. Hold on a sec. What side is that? There's two pieces to it. That one is what does it start out? Section 4?
This is 5.
Or section 5? Yeah, there's the other piece.
Thank you.
Okay, so on the first page, on section 5, says determine the atomic weight or the average isotope of each element given in the following information. So the first one says naturally occurring silver. So silver 107. Oh, that was weird. Silver 107. What does that 107 mean again? That's the mass number, right? That's how we differentiate the different isotopes. And that represents 51.84% of all silver. And then silver 109 represents 48.16% all silver. Okay? So we got to figure out what the average is. And since these are different percentages, we can't just add them up and divide by 2. Does that make sense, guys? Okay? So this isotope has a mass of 107, so we're just going to 107 multiplied by the relative abundance, or just the percentage written as a decimal. So to do that, we divide by 100, right? Because percent means per 100, yeah? So it's going to be 51.84 divided by 100, or move the decimal place 2 places to the left. It's going to be 0.5184. And this relative abundance is 0.4816. Okay so far? Okay, so we're going to multiply 107 by its abundance. Relative abundance is 0.5184. And then we're going to add to that 109, multiplied its relative abundance of 0.4816. And we do the calculation there, and we get 107.96. Good? Now, does your book talk about AMU yet?
Yeah.
Okay. Does anybody know what that means?
Atomic mass.
It means a bunch of junk. No, really. Why we still do that, I don't understand. Well, let me just tell you. It stands for atomic mass unit. Okay. The length of this table is 5 distance units. That's not useful, is it? Okay. So rather than putting AMU on here, I'm going to tell you what it really is. Oh, but we're not going to talk about moles yet. It's okay. We could talk about it and then talk about it again. Is that okay? All right. So this is 107.96 grams per mole. Because if you think about it, the mass of an atom isn't 108 grams, right? It's not. But it is 107 about 108 grams for 1 mole of that substance. We'll talk about that later. You don't need to know about it right now, so don't freak out about it. But that's what the atomic mass unit is grams per mole. Good? And, well, that kind of looks like a what? A conversion factor, doesn't it? And that's what we'll use it as in chemistry. Good? Does that make sense, or did you? Okay. Anything else? All right. Yeah.
Can you do the answer of the second one we just did? So
Yeah.
I can see if I got it right on my own.
Yeah. The answer is 10.80 grams per mole, or AMUs, whatever. Okay. Any questions on that? Did you get it?
I don't know.
Oh, okay. So
I had
you.
to get my calculator out. I
Good.
did all the work except.
Oh,
doing it, and
perfect,
I couldn't
perfect.
find my calculator.
Yeah. Let me know if you.
I just wanted to check it.
No.
so I could see.
Perfect. Perfect. Anything else? And sorry, I sounded a little bit negative there, singing AMU's junk, but whatever. Okay, that was just, had to get it off my chest. Now we're good. Okay. Anything else? Okay. Let's continue then. Do we need to review the different groups or different classes of elements? Are we okay with that? Okay. So today we're going to start off with the electron configuration. But before we do that, I'm going to pull up a periodic table. No, not that one. Yeah, let's just go ahead and get started here. So the electron configuration.
Is this the one we can write on, or is this for?
Yeah, that's yours. When I printed those out, they printed wrong way, so sorry I printed it so small. On the test, it'll be full page like this, okay? Sorry about that, but I didn't have time to print it again, so. All right, so electron configuration. Why are electrons so important again? Who can tell me? You remember from last time? Yeah.
Electrons are important because they determine the interactions that happen, or the chemical bonds that the atom form.
Oh, that's right. The only part that changes in a chemical reaction are the electrons. Okay, nothing else. So we kind of have to understand how they're structured or how they're arranged around the atom to help us know a little bit more about their properties. Okay. Let's see. And we're going to go through this real quick, guys. This is like learning Chinese. I said that once before. It's like learning a language where it's kind of difficult at first, yeah? But as you look at it, you can come to it a little bit easier than a language, but okay? So it's just a code to kind of to tell us where these electrons are on the atom, okay? And so I'll try to help you understand as much as I can. And the reason I say we're going to go quickly on this, because it's not huge in this class, okay? But just give you a foundation knowledge of it. All right, so before we talk about the electron configuration, and you can even write on your periodic table that I gave you. You see how helium looks like it should fit right there? So this group is called the S group. And we'll talk about what that means in just a minute. Okay. The rest of the main group elements, so the red and the blue, remember from last time? Did we talk about the main group elements last time? Okay, these are the main group elements. This is the P group. This is lowercase s, lowercase p. And then, what are these metals called again? Transition metals, because they transition from main group to main group, okay? And these are the D group. And this bottom section right here, the inner transition metals, this is the F group. Okay? Now, good. Some of you taking pictures of that? Yeah, do that. That'd be great. We're going to consider this periodic table, not the periodic table of elements, but the table of electrons. Okay? So we're not going to ignore the elements completely, but for example, this is electron number 1, this is electron number 2, and this is electron number 111. Are you with me? Or just number of electrons. So we're ready to move on up past this? So we kind of need to know that. Okay, so the electron configuration. So let's deal with hydrogen's electron configuration first. So remember we talked about the Bohr model of the atom? So for hydrogen, the Bohr model looks like this, right? Where we have the nucleus, which is consistent mostly of, for most hydrogen, is just 1 proton, 0 neutrons, right? And we got 1 electron. But I'm going to keep it simple here. So that's the Bohr's model, and we're just interested in these electrons here. And so how we do this, we're going to just call the electron configuration for hydrogen is 1s1. And let me try to explain where we get these numbers. It's kind of like your childhood language that you made up with your friends, right? You make this so no one else can know what you're talking about, but okay. This is kind of like that. And I'm going to show you how to read it. We use the periodic table to read it, okay? So this first number, that is the energy level, or the shell. Okay, so remember we talked about the fan blade, and the electrons are somewhere in that area. Do you remember this? Or do I need to talk about it again? Okay, so it's in a general area somewhere in that region. Okay, that region is like the shell, okay, where the electrons are. And in fact, there's a little bit more to it than that. We'll just, okay. So that's the energy level. And we talked about Bohr says electrons have a specific energy level, right? So that's what it is, okay? And if we look at the periodic table, here are the energy levels. Energy level 1, 2, 3, 4, 5, 6, and 7. Those are the different periods, right? So energy level 1 consists of the entire period 1. Good? And we can see hydrogen, the first electron, is in energy level 1, right? Okay, the S refers to the subshell, we call it. And Well, here you have subshell S. Here you have subshell P, D, and F, right? So the first electron is in subshell S. You with me? And then this right here refers to the number of electrons in that subshell. And it looks like an exponent, but it's not an exponent. We're not math. It's just a way to write it. Yeah. Is everybody following so far? Okay, helium. Let's do another one. How many energy levels do we need for helium? Just one. So the first two electrons are on energy level 1. So here it is, 1. And what subshell is helium a part of? S. So electron 1 and electron 2 are part of the S subshell. So we're going to say S, and there's 2 electrons. Okay? Should we jump a level down? Well, that's okay. And I'm not going to do every single one of them up to there. I'll just kind of give you the basic idea. So lithium has 3 electrons. Where are the first 2 electrons on helium's atom? On what energy level? On the first energy level. Electron number 1 and electron number 2 are always going to be on the first energy level. Always. And we got to always start with 1. When we count, we always start with 1, right? So when we talk about element number 111, the first 2 electrons on that atom are right next to the nucleus on energy level 1. On that first ring. You with me? So we have 2 electrons. Oh, I forgot to draw the electrons here, didn't I? Whoops, sorry. So helium has 2 electrons on that first energy level. And lithium also has 2 electrons on that first energy level. Good? But then on the second energy level, right here, whoops. Lithium's third electron is on energy level 2. So here's our energy level 2. And we have 1 electron there. So that's going to be on energy level 1. What subshell is energy level 1 have? Just S, right? So electrons 1 and 2 are still on the 1s level. Are we good? Then we go back to our third electron. Now is on energy level 2. And what subshell is electron number 3 on? It's still in the S. Do you see that? So we're going to say 2s. And how many electrons are in the 2s level?
1.
Just 1 of them. And that's a total of 2 plus 1. That's 3 electrons. You kind of getting the hang of it? Yeah, question.
Can you say that one more time?
Should I do another one to explain it? All right. Yeah, this is, like I said, this is tough right at first. But if you get it down, it's really not that bad. Okay? So let's do neon. I'm going to go way over here. Is that okay? So let's do neon. And how many electrons does neon have? When we say how many electrons, I'm talking about neutral neon. What would you say? 10. It's atom number 10, so it has 10 electrons. 10 electrons, 10 protons, right? So that number, the atomic number, represents the number of protons, so you don't get confused, right? But if it's neutral, it has the same number of electrons as protons. Are you with me? Okay? So we got on the first energy level, electron number 1 and electron number 2. We still have to count at number 1, right? We got 2 still. It turns out there can only be 2 on that first energy level. Any ideas why? Electrons want to be as far apart as they can. They repel one another, right? So if we try to put another one, there's too much repulsion going on there, and it doesn't work. So we can only have 2 on that first energy level. And if we look at the periodic table, we can see that. There's only 2 electrons on that first energy level. How many can the second energy level fit? Can you? 8. 1, 2, 3, 4, 5, 6, 7, 8 of them. Are you following me? Okay. Erase this to make it so it's not so messy. Okay. All right. So then, the next electrons on energy level 2, we have 8 of them you mentioned, right? So we're going to have 1, 2, 3, 4. And ladies and gents, this is not how an atom looks, but this is just Bohr's model. They're paired up and far apart. Okay, this is just an easier way to show what's going on. This is not how they look, okay? Well, in reality, I don't know how they look exactly, right? Okay. So this is going to be what? 1, S2, 2S2. Good. I kind of skipped a bunch of elements, didn't I? But then the electron 3 and 4, there's only 2 electrons in the S subshell. You with me? You can only fit 2. 1, 2. You can never fit more than 2 in the S. Does that make sense? Okay. So it's going to be 2S2. And after number 4, we got 5 through 10 are all in what subshell? The P, but it's still on energy level 2. Good? So we got 2P, and we're going to count them. 1, 2, 3, 4, 5, 6, until we get to neon, right? Because that's what we're doing. Does that make sense to everybody? Did that answer your question, Nancy?
Yes.
And ladies and gents, I am not going to worry about anything past calcium, because then it gets weird. Okay? Are you okay with that? So could you do calcium? Try calcium on your own. And you don't have to draw this. I'm just drawing it to show you kind of what it's showing. So here, let me just show one more thing. In energy level 2, we have 2 plus 6. That's 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay? That's it. Yeah.
Do you want to do all the S's first and then the P's?
Nope, you do in order.
In order?
Yep. Number order. Always. Okay, so let's do calcium. Or you should do calcium. This is the longest one. I'm not going to say hard. It's all the same. But it's the longest one I would ever have you do. Should you spend a lot of time studying this? Probably not. Okay. If anybody's struggling, please let me know. Because this is kind of hard at first. It really is. Who needs more time? Who wants more time? Should we do this? Okay. Tell me, what is it going to be?
1S2.
1S2? No, not all of you, just one of no, yeah, all of you. No, I was kidding. Yeah, keep going.
2P6. 3.
So you said 1S2, then what?
2S2.
2S2,
2P6.
2P6,
3S2.
3S2,
3P6.
3P6,
4S2.
4S2. That's it. Should we? Yeah. Okay, so I'm going to write that up here so I don't have to keep going down. So we got 1S2, 2S2, 2P6, 3S2, 3P6, and 4S2, right? Here we go. So the first two electrons are on energy level 1, subshell S. There it is, 1s2. Are we good with that? The next two electrons are on energy level 2, subshell S, and there's 2 of them. There we go. You following? If you get lost, then say something before I get to the very end. Say, oh yeah, can you just start over? Right, I want you to stop me before we get there. Yeah.
So are you just going down?
I'm going in number order.
Oh.
Yep. So far, I did 2, 4. I'm on electron number 4. Now, the next 6 electrons are 5, 6, 7, 8, 9, and 10. That's 6 of them. And they're in section P, but on energy level 2. So it's 2p6. Are we good? Then,
Wait, sorry, didn't you just do, energy level 2?
yep, it's still energy level 2. That's why it's 2 right there. And then it's P.
Now you're in P.
Yeah.
Okay, yeah, okay.
Are we good?
Yes.
Yes, thank you for stopping. Okay? And then we have 6 of them. And that's so far, that's 10 electrons. We got to eventually count to 20, right?
Yeah.
So what's after 10? 11 and 12. Why do I do 11 and 12 separately? Because they're an S. And what energy level? 3. 3S, and there's 2 of them. And then after 12, you got 13 through 18, which is 6 of them. So that's 3p6, because it's in group P. Are we good?
Yeah.
And then after 18 is 19 and 20, so that's 4s, and there's 2 of them. Just go in number order, that's it. You just have to remember S, P, D, and F, right? Well, you don't, because we're not going to do anything past 20. Are you okay with that? And so, why? Why? Let me show you why. Okay? So, we have helium and neon here. They have something in common. What do they have in common? Their energy level is completely full. Yeah? What about argon? What would it look like? Also full. And what about krypton? Xenon? They're all full. There are, in fact, it's kind of like having a balanced tire. You guys ever rode down the highway with an unbalanced tire? It's like, or you maybe something sticking on your tire, like, boom, boom, boom. So it drives you nuts, right? Well, if your energy level is full for the atom, then it's going down the highway with a nice balanced tire. Okay? If you're missing one, kind of like, let's say, fluorine is going to be what? 1s2, 2s2, 2p5. Oh, we just need one more on that second energy level, right? And so it's like, boom, 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 and it's just off balance. Saying, come on, let me just have one more, right? Give me one more and I'm going to be like a noble gas. Do you remember we talked about these halogens last time? These guys right here? What did we say about them? They're the most reactive nonmetal. Why are they the most reactive? They are almost there. It's driving them nuts. They just, come on, just give me one, give me one. This group right here, oh, they're missing two. It's still icky, but it's like, okay, I still got a ways to go. I'm not saying, come on, just give me one more, just one more. Right? They have two. So they might be a little bit more reactive than the rest of them, but do you get that? What did we say about this group right here? These are the alkali metals, and these are the most reactive metals. Do you remember this from last time? Maybe we should study this.
Very quickly.
We did. I apologize. Do we need to go over that again?
Sure.
Okay. Yeah? Okay. And let's see. Come on. All right, these guys right here are the alkali metals. They're the most reactive metals. Okay. Does it make sense why they're the most reactive now a little bit? So let me do this real quick. So lithium has one electron on the outer shell, on the highest energy level. If we do sodium, it looks like this. 1, 2, 3, 4, 5, 6, 7, 8. Right there. That has one electron on the highest energy level. And so what are these guys doing?
Trying to get rid of it.
Yeah, if I could somebody take it. It's driving me nuts, right? Just take one and I'll be happy. And then I'll be just like a noble gas where it's just balanced, right? Does that make sense? And this is just an analogy, ladies and gents. You with me? Okay? They're not really screaming and, okay. Okay. And if you look at all of these elements in group 1, it has one electron on the highest energy level. Just one. That's why they have similar properties. Because they just have one, just like all of them. If they could just get rid of that one, they're going to be good. Good? Then we got the second group. which are the alkaline earth metals. And then you got, oh, that's the wrong color. These guys are the noble gases. And what did we say about the noble gases?
They're balanced.
They are balanced, but they're the least reactive elements because they're good. They don't want any more electrons. They don't want to give any electrons. They are good, all balanced. Does that make sense? Least reactive elements, not just metals or nonmetals, but least reactive elements on the periodic table. Are we okay with that idea? Okay. And then this group right here, these are the halogens. And these are the most reactive nonmetals. Because they just need to get one more. Okay? How you feeling? And then this group right here is the transition metals. And this group right here is the inner transition metals. Good? Do you remember why we call them inner transition? Because they fit right there inside the transition metals. Did we talk about that last time? No? Oh. I just rushed you through, didn't I? Ah, sorry. We shouldn't have done that. Okay. So if you look at this, this is 57 and 72. What? 58 and 71. Do you see how it goes? Fits right there, in between there? Okay. That's why we call them the inner transition metals. Same thing here. We have 89, 104. This is 90 to 103. Good? All right. Is that good enough? Can you take a picture of that? Or are we good? Or all right. Any questions about the electron configuration? There's more to it than that, and I'm not going to, no, we're just not going there. I just mostly wanted to kind of get an idea of what it is and why elements are grouped the way they are and what happens in the periodic table. The properties repeat, right? Did we talk about that last time? So a periodic table is called periodic because the properties repeat. Anything periodic is something that repeats, right? Okay. So we've got a property here, and then it goes through, and then the next period, it repeats that property. They're not exactly the same, but they're similar. And I can show you sodium today if I can find a container, because I forgot to bring a container. I might have to cut the bottle. No. We'll find something. Okay. This one's, I'm getting sick of this one anyway, so maybe. Good? Any questions so far? We feel good with the electron configuration? Okay. And again, that's not a big part of what we're going to do in this class. Okay? But I mostly just wanted you to understand that a little bit so we can understand why the properties repeat and why they're the same. Yeah, okay. And so that the electrons determine what the properties are. Okay? Okay. Let's talk about one more thing or two more things. And then we're done and we can review a little bit. Okay? Yeah.
So you said periodic means like it repeats itself?
Uh-huh.
Okay.
Yeah. Yep. So like the Earth's period around the sun is a year. And then what? It does it again. It repeats again and again and again. And the Earth's period around its own axis is 1 day. And then does it again and again and again. Periodic. When you was in high school, you had class periods. Your first period was maybe 190 minutes. And then the next period started again, 190 minutes. 190 minutes, just repeated the time. Yeah? But this periodic table doesn't repeat time, it repeats what? Properties. Good? Okay. Let's talk about the most important electrons of all. We kind of already did that, but now we're going to give it a name. Valence electrons. And these are the electrons that are the only ones that are affected in a chemical reaction. Where are they? On the outside, right? So the electrons in outermost shell or energy level. Good? And this is why lithium, neon, magnesium, potassium, rubidium, cesium all have similar properties because they all have one valence electron. Good? So let's get another periodic table here. And on the periodic table, there's a way to tell without doing the electron configuration how many electrons are on that, how many valence electrons an atom has. Okay? So hydrogen only has one electron period. So it has one valence electron, right? What about lithium? One valence electron. What about sodium? One. Potassium, one. Rubidium, one. Cesium, one. All of them just have one valence electron. There it is. So these are the valence electrons. How many does group 2 have? Two. And we're going to skip past, we're going to just talk about the main group elements. We're going to skip past the transition metals until next unit. How many does group 13 have? Not 13, but 3. 3. And what about group 14? 4. 15 has 5. 16 has 6. 17 has 7. And 18 has 8. Except for helium only has 2 total. Remember, on that highest energy level, you can only fit 2 on the first energy level, right? So it only has 2. Are we good? And all of these guys, everybody wants to be just like a noble gas, right? Everybody wants to be noble, for example. Yeah? So we have something called the octet rule. So atoms tend to gain or lose electrons to achieve a noble gas configuration. When I say configuration, I'm talking about electron configuration, yeah? And what we're talking about is that full energy level on the outside. Full valence shell, we call it. Good?
I have a question about the valence electron.
Uh-huh.
So, can there only be 8 on the outer shell? For what we're learning at least?
Yes.
So, for the, on the periodic table, 9, 10, 11, and 12,
So these guys right here?
yeah. But they're just, that would be the valence electron?
No.
It
Nope.
gets more.
Or
Yeah,
is it
it,
going to be,
we're going to get into that next unit.
okay.
And the only thing you can read on the periodic table is for the main group elements. The rest, I don't even know what they are unless I know what it's with. And I'll show you how to do that. We're going to talk about that next unit, but not right now. Good? Great question. Anything else? All right. Let's see. I think that's all I want to cover there. And now we got one more thing. And that is trends on the periodic table. You guys understand what a trend is? Does that mean everything has to follow that trend? No. Right? What's a trend these days? Yeah, pretty much anything goes, right? Back in the 80s, it was your high shorts and your holey jersey shirt, or maybe your belly, right? Remember that? And your high top. That was the trend. Everybody was doing that. Okay. 90s, you got the new wave going on, and or was that earlier? I don't remember. Earlier?
Wait, the 90s were a part of it.
Well, the 80s was, yeah. You just comb your hair straight back and it dries. And okay. Anyway, those are trends. But did everybody have that style? No, they didn't. Okay. So same thing here. I'm going to show you a trend, a few trends. Doesn't mean they followed exactly, but luckily on this page right on the back side of your periodic table is one of the trends, and it's not a trend. They give you the exact values, right? I don't know if they're 100% in stone, but okay. We'll just start from here, okay? So, should I use a new periodic table, or is this one okay? Okay, so the first trend is the atomic radius. Now, what's the shape of an atom, basically? Circular, right? So the radius is from the center, the nucleus, to the outermost electron, the valence electrons, right? So we're pretty much just saying the size of the atom. You with me? Okay. So let's use yellow for this, atomic radius. Or we can just say the size of the atom, right? As we go from top to bottom, what happens to the size? Any ideas? It gets bigger and bigger and bigger, like we see here, yeah? More energy level just piles on, and it gets bigger and bigger and bigger. Make sense? So that one's pretty easy to understand. Increase is going down. What about going from going from left to right? The energy level doesn't change, so it kind of just looks like it stays the same, but it doesn't. Because what does change? Number of what? What does that number represent? No, well, it kind of represents electrons, only for neutral atoms, but mostly that's the atomic number, right? Which is the number of protons, right? we have more protons as we go to the right. So think of, can you guys understand how magnets work a little bit? Okay. You get a strong neodymium magnet. That's like fluorine, for example, because it has 9, right? And you have lithium with only 3. That's like a fridge magnet, right? Real weak magnet, okay? And, well, if you bring metal towards them, and the metal pieces are like the electrons, what's going to happen? What's going to be pulled tighter, the fridge magnet or the neodymium magnet? Neodymium, it's going to pull it in tighter, tighter, and tighter. So it's actually a little bit smaller as it goes from left to right. Does that make sense? Not a ton, because it's only the difference between 3 and 9 electrons, or protons, right? So it decreases, let's use the same color, decreases from left to right. Yeah, so because as it goes from left to right, the magnet gets stronger, so it goes, pulls it in just a little bit tighter. Good? Was that a good analogy? It's not how it really is, but basically, right? If you want me to give you an equation, I can. Anybody want it? Okay, I won't. But anyway, we'll just keep it at that. Oh, please let me, it's so cool. Okay, I'm just kidding. All right, so the next one is the electronegativity. And this is more important, I think, for this class. Electronegativity. And the electronegativity is the ability of an atom to accept electrons during a chemical reaction. I don't know if you can read that. Is that kind of hard to read because it's on the periodic table? Okay. And I'm going to just use the blue color this time. So from left to right, which atoms tend to gain electrons more? Lithium or fluorine? Fluorine. Which one wants to gain electrons? Remember, this guy has 1 valence electron. This guy has 7 valence electrons. And how many do they want? 8. So who's going to say, come on, just give it to me? Fluorine is just 1 away. What's lithium going to do? You can have it, right? Take it away. Because it's a lot easier to get rid of 1 than to gain 7 more. You with me? Okay. And so the electronegativity does what as it goes from left to right? Increases, right? Does that make sense in your mind? And what about from top to bottom? So top to bottom, they get bigger and bigger and bigger, right? And those valence electrons that it's going to get rid of or accept are going to be on the outside, right? So as we go down, we get a stronger magnet, right? But it gets farther away. We take this strong neodymium magnet. So we grab my keys here. Neodymium magnet, and you put it right here. Come on, pick it up, pick it up. Is it going to do anything? No. You get that fridge magnet and you put it right here. Which one's going to have a greater attraction? The fridge magnet, because it's a lot closer. Okay, and that's kind of like you look out there at the mountain. Can we see it? No, because there's smoke. And you look out there and It's like that big, right? Is it really that big?
No.
No, but it looks that big. Let's say you get twice as close. You get in between here and the mountain. Then you look at it and it's what? Whoa! Like a lot bigger. So distance is a bigger effect than strength. Does that make sense? And if you want, I can show you that equation and it'll show. No, okay. Just kidding. Okay, so as we go down, it decreases, right? Any questions on the trends? Yeah,
How come on one side you increase and on the other side you decrease?
because we're talking about two different trends.
Okay,
Yeah. And do you understand those trends though?
yeah.
Okay. Now, can I see that real quick? So on this, you get this for every exam. It has the electronegativity values of all these elements. So probably won't be very useful on this exam, but we'll get next unit. It's going to be very useful. Okay. Any questions? Okay, let me make sure I got everything. Yeah, I think we're good. So that's all the material for exam 1. What would you like to review? So we have introduction to chemistry is like the scientific process. And remember, just to kind of get on the top of your brain, can you conclude anything you haven't tested? You cannot. So that's what one question will ask you. It won't ask you that simple, but it'll give you an example and say, what can we conclude? And you're going to have to do multiple choice and choose the best one, right? Okay? And that's all I'm going to say about that, unless you have questions. Okay, then we got matter. Pure substances, mixtures, homogeneous, heterogeneous. Any questions about that? Yeah.
How similar is the practice exam to our actual exam?
Oh,
It's
pretty
pretty close.
close.
Yeah, it is.
So, yeah, did you guys make sure you do that practice exam? I've had students that just wait till the end of the semester. Can I still do those? What? Why? I mean, sure, I'll let you do it to get the little points, because you get 2 tries, right? But it's going to help you the most if you have it down before you go into the exam. Okay? Did anybody go through that practice exam yet? Okay. So go through it and let me know if you, next time we meet's exam, I guess. Okay, the next part, numbers, yeah.
I do have a question.
Uh-huh.
Can you go through the 2 types of physical properties, the intensive and extensive? I have a hard time understanding.
Yeah. So we got intensive versus extensive. So intensive properties are going to be properties that tell us what material we have, tell us what kind of substance we have. So this determines the type of substance. For example, the color, let's see. Yeah, the color is an intensive property. Because copper, we could recognize copper by its color, right? Or its density. We recognize it's gold rather than fool's gold by its density. So that's an intensive property. But an extensive property, it's just kind of the I mean, I don't know, what's a good way to say that? Well, let me give you examples. That's probably best way, right? Someone's dying. Sorry. It's my glucose levels. Just turn that off. I'm not dying, I'm just kidding. But sometimes my sugars go low and I have to grab something, so, but I don't need to right now. They're a little high, so I might have to pee. Sorry. Always something with this guy. All right. So anyway, so extensive properties are things kind of on the external, doesn't describe what the substance is, like its shape. Is copper always round? No, just in the form of pennies, right? Or a coin. Not really only, but mass, again, if it's 5 kilograms, does that tell us it's copper? No. Does that make sense? What about the melting point of, what if its melting point is 0 degrees Celsius? What does that tell us it is? Water. Water. That's intensive. Does that make sense?
Yeah, it does.
Great. Anything else? Okay, we got scientific notation. We got SI units and the prefixes. We got significance, accuracy, precision.
What about the homogeneous and
Heterogeneous?
because I kind of get it, but some of them I would say is the opposite.
Okay, you tell me which ones.
So for example, like here I have homogeneous one is like Kool-Aid. That's one of the examples. And then I don't know. in
And
my
you think
brain-
that's heterogeneous?
I don't know.
Okay, is it because you've never had Kool-Aid?
Yes. I've had
Okay, Kool-Aid is just a punch. Have you ever had fruit punch or
No.
anything? That's basically what Kool-Aid is. Okay,
But-
and it's the same it's the same throughout, right? You don't see chunks anywhere in there, and it tastes the same no matter how much, right? It's just all the same. Does that make sense?
Yeah.
Okay, what
I
else?
just get a little not confused.
Uh-huh.
It's just like concrete is a header one or blood. It's like you also can't see the particles. But
Yeah,
I
so-
know
so blood-
is different.
Yeah, and that's the same thing with concrete.
Yeah.
If you've never poured concrete or broken up concrete,
It's like
it looks the same,
but
right?
it's not.
But inside it's not.
And Kool-Aid is different because it dissolves.
And what?
Water.
Kool-Aid?
Is different because it dissolved. Like
Well, the sugar dissolves in it, right? Or the packet dissolves in water. And since it's dissolved, kind of like salt water, if you ever been to the ocean, or that's probably where you
Yeah.
drink salt water, right? It's the same throughout. You come over here, it's like, oh, that's a little bit saltier. Let's come back. No, it's all the same,
Okay, consistency. Okay.
right? Same with the air. The air's pretty consistent all the way through. And the reason it is because it disperses and just kind of fills space, right?
Got it. Thank you.
Anything else? Yeah,
Prefixes?
prefixes. So, do you want to go through all of the prefixes again? Okay, we can, definitely. So, I'm not gonna draw that table. You guys have that in your notes? It's, prefixes are just something you're just going to have to stick here, memorization. Go over and over and over and over and over and over, and you feel like you got it, go over it a little bit more, just to make sure you get it, right? So, some of the main ones, I'm gonna give you just the main ones that we use. I'm not saying the other ones won't be on there. So know them all. But you got kilo is common. Kilo means what? 1,000 or 10 to the third power, right? And then centi's probably good to know. and that is 100th from 10 to the negative 2, right? And again, I mean, it's kind of like, do I know everybody's name in here? Almost. I don't quite have everybody yet. And, but that's what it's like, trying to memorize everybody's name. You just got to make it up in your mind, that's what you're going to do. And you got to do it. You got to put forth the time and effort and get it down. Again, so here's my, if you don't have it down right now, you might want to put some of these on your little note card, right? You can make a new note card next exam, so maybe between now and next exam, you get them down, right? You take a little bit more time and get those down. So put whatever you need on your little note card that you're just, you know what, I don't have these down, so I better have them, right? You do what you need to do. Does that make sense? And then milli is 0.001 or 1 over 1,000, and that's 10 to the negative 3. That's a common one. That's probably the most common. So make sure you have that down. Micro, probably a good one to know, is 0.12345 and a 1, or 1 millionth, 10 to the negative 6. Okay. Anything else there?
Could you do like just one example with
Of metric to
converting?
metric?
Yeah.
Yeah.
Because it's,
Yeah, you bet. Okay, so let's do, what do you want to convert to?
like something that I got at home was centi, 1 kilo to centigram.
Okay, so 4.25 kilometers, or kilograms rather, to centigrams, right? Do you want to use the dimensional analysis method, or do you want to use the metric to metric method that I showed you? Your call, you're asking the question.
I don't know, I usually do step by step. That may be too much.
So you mean dimensional analysis?
Sure.
Okay, let's do it. And we can do both if you decide you want another method here. So if you don't have this down, maybe write it on your little note card, right? So 4.25 kilograms. And we don't want kilograms, so where do they go? On the bottom. And we know kilograms to what? Gram, just grams. I don't know how many kilograms are in a centigram or centigram in a kilogram, right? I don't know that. But you could probably figure it out. But I would just go with what we know, yeah? So we know there's how many and how many?
1,000 grams.
1,000, good, 1,000 grams in 1 kilogram. Kilo means 1,000. So everybody watch this. 1,000 grams, 1,000 grams. Same on top, same on bottom, has to be. So make sure you know that, okay? If they're not the same, if you're just guessing, you might want to write them down on your card, okay? So kilograms goes away. We're not there yet, so we keep going. Grams goes on bottom because that's not what we want. We can go grams to centigrams. How many to how many? 100 what?
2 ones.
Yeah, 100 centi. What does centi mean? 100th. 100 100ths of a gram is the same as 1 gram. Do you get that? Okay. And that goes away. And now we have centigrams, that's what we're looking for. So it's 4.25 multiply 1,000 multiply 100. We don't have to worry about the ones because they're just ones. Are we good? Does anybody want the other method?
Yeah, I feel like it's easier.
Okay, So I'm gonna go through it, and if you guys like that, you just, oh yeah, that's great. Then stick with what you're good at. Stick with what you know, okay? But sometimes you know what? I just don't know if I'm gonna be able to know how many, I just don't know how to read those icky yucky numbers, right? Maybe that's what it is, okay? So we're going from kilograms, so 4.25 kilograms to centigrams. So kilo means what? 10 to the third power, so I'm going to write the 3. Minus, it's always subtract, always, always, always. What does centi mean? 10 to the negative 2. 3 minus a negative 2 equals, yeah, this means plus 2, that's 5, right? So that means it's 4.25, I just took that number right there, times 10 to the 5th power, and that's it.
Oh, that's so easy, yeah. What?
So, yeah, you pick your method. And this is going to be centigrams, right? But if we do this, times by 1,000, so 4.25 times 1,000, 1, 2, 3. And then times by 100, 1, 2. And if we write it in scientific notation, 4.25 times 10 to the 1, 2, 3, 4, 5. Same thing. Either way.
So the exam, we can write it both as like the whole number or the scientific?
Well, it's multiple choice.
Oh, okay.
So if it's in scientific notation, then that's what you need your answer in, right? Are we good?
Thank you.
Mm-hmm. Yeah. Anything else?
Wait, so what would be the answer?
Right here.
Okay.
Or you can say 425,000, so 425,000 centigrams. They're both the same number, right? So what answer should you use? Whatever answer is in your multiple choice. Okay? Anything else there?
Can you do this with any question right here?
No, this is for metric to metric only. So this one right here, you mean?
Yeah,
Yeah, that's metric to metric only. But the dimensional analysis works for everything.
okay.
So my preference, I like just one method. But that's me. But after showing this way, because at first I had to think, okay, now what's an easy way to do this? So you think through it, it's like, okay. And then you do it a few times, like, okay, yeah, I could do this. But that's what it is with whatever way you do it. You just got to be familiar with it. That's it. Okay?
You said we don't have to memorize the Celsius, the Fahrenheit.
Can I see that?
It's in
It's right there. And I'll give you that on every exam. I'll give you this
wait, where?
whole thing except for this is going to be turned and made bigger.
No, yeah, but where?
I see the Kelvin.
So,
Yeah, it's Kelvin. I don't
Oh,
know.
s-
The Celsius.
so what did you ask?
So the Celsius and Fahrenheit. You said
Oh.
you gotta know it in the exam.
No,
Oh, we
that
don't.
one right there, if you want to not do that one, just use Google. That means I'm not going to test you on it.
Because it was like 20 questions about it and they don't want. That's
Oh,
why-
really?
Yeah. there
Did
was
you
a
use
lot.
Google?
Yes.
Oh, good.
You never know.
Yeah,
I can't use Google in the exam, or can I?
you cannot. And that's
Okay.
why I will not give you that on the exam.
Just want to make sure.
No, what we should do is just get rid of Fahrenheit,
Yeah.
but we won't.
I mean, everywhere else did.
Yeah. Anything else? What about dimensional analysis? How are we on that? Yeah, like some dosing problems or
Yeah, if you do an equation where it's like 135 pound person, you can dose this much.
yeah.
That
Yeah.
calculation.
That one.
Yeah.
Okay, I'm just going to use those numbers because you thought of them. Why do I have to? 135-pound person, and the doctor ordered him to take 300. Let's just say 500 pounds. 500 milligrams of a drug, whatever kind you want, okay? I'm penicillin, great. Milligrams per day, okay? And the formulation of this, so you go to the pharmacy, and, well maybe there's two formulations, but your patient, I just can't take any pills because I can't swallow. I throw up every time, whatever, right? So you want to inject them, right? So you have to have a solution. Maybe the solution is 100 milligrams per 5 milliliters. So we want to know, well, how many milliliters should we give this patient per day? Does that make sense? Okay? Because maybe they're an inpatient at your hospital and you have to give it to them, right? So how much should you give them? So where should we start? We know what we're looking for, and we know what we have. So where should we start? One of those. We should either start here, here, or here. Yeah.
Could you add a per 500 milligrams per, like, 20 kilogram body weight or whatever?
So say that again.
Could you add, the dosage is,
500
milligrams per
certain kilogram.
body
Oh, yeah.
weight.
Oh, we would need to do that, wouldn't we?
Yeah.
Yes. See what happens when you just pull it out of your brain? Especially when you're not a doctor person. Okay. So, yeah, per 30, that's a lot. That's going to put a lot, right? Let's just change this. And it doesn't matter if it's real or not, but because it's the same way. So let's say 30 milligrams per 20 kilograms of body fat. Yeah, thank you. Otherwise, that wouldn't have made any sense. Okay. Yeah, okay. So where do you want to start? That looks like a conversion factor. That looks like a conversion factor. Let's start there. Now, you don't have to do it my method. You can start at any one of those you want. Okay? So 135 pounds. What are we going to convert to first? Kilograms. How do you know kilograms?
It's 2.2 pounds of body weight for every 1 kilogram.
Yeah, we got kilograms right there, right? And we don't have pounds anywhere, so let's convert pounds to kilograms. So 2.2 pounds to 1 kilogram, right? And then, are we going to, so we use that one, are we going to use number 1 or number 2 next? Number 1 has kilograms in it. This has kilograms, and we don't want that because we want milliliters. Kilograms to milligrams we can convert it to. You with me? Because that's what our given information tells us. 30 to 20. So Aiden, I think, calculated, you reduced this, right? Maybe you did that in your head. I don't know. I would go with whatever they give you. Don't try to make it simpler, because how many times do we make a mistake with something like that? It's like, I'm just saying, I've done it. Everybody's done that. So use what they give you.
That is the number that they'll give you for that conversion rate. I just haven't memorized because it asked a couple times during the homework.
So you mean,
For the kilograms to pound, is that what you're saying?
oh, no. Is that what you were saying? Okay, sorry. I wasn't paying attention. All right. So, but anyway, so we could probably do that in our head. Oh, it's just 3 to 2. Rather than trying to do that, is what I'm saying, is just leave it how it is, right? Use what they give you, okay? So that we don't make a mistake in our head, an unnecessary mistake. So now we have milligrams. We use that one. Now we just have one left, and it has milligrams to milliliters. And we're going to milliliters, so that one works. So 5 milliliters to every 100 milligrams of drug, penicillin. So that goes away, and we're left with that. That tells us we're done. And that's it. Well, multiply and divide, right? Are we good? Do we need an answer? Okay. So 135. Divide 2.2. Then what? Times 30. Divide 20. Times 5. Divide 100. Do you all understand this process?
So the conversion rates can flip-flop however you need them to be?
These guys?
Yeah, like how you put.
Yeah. So this one right here, we flipped it upside down, didn't we? Because if you think about it, if we have 5 milliliters of this solution, it has 100 milligrams of penicillin, for example. Or if we have 100 milligrams of penicillin, it's the same as 5 milliliters. They're the same. Does that make sense? Kind of like 12 inches over 1 foot is the same as 1 foot over 12 inches. Anything, yeah, that's just a conversion factor, so we can flip those. So the only thing I would say watch out for is if you start with a conversion factor, which you can, make sure you start with the one that's going to help you. If I would start with one, I would start with that one. Why? Because it has what we're looking for in there. And then I would flip it so that the milliliters is on top. Because I'm looking for milliliters equals something, not 1 over milliliters equals something, right? I don't want that. Yeah, Sky.
When we get a decimal answered, what did you say about rounding? Because you were saying something about rounding medicine could go bad. if
Well,
it's like-
it all depends on what it was. And I think on that last example, a student from my other class says, with this drug, it doesn't matter how much you take. It's just like a antibiotic, and I don't remember which one it was, but he says it doesn't matter. So if you're at 2.7 tablets, it's okay to round to 3. But if it was like a painkiller that's going to give you addiction, get you addicted on it, and yeah, you don't want to overdose on it, right? But so you just have to know your medicine.
Flexible with our rounding.
Yeah, yeah. So I'm going to have you round. So like this, we have. So our answer. What's our answer here? Did anybody calculate it?
60227 with 27.
Say that again.
4.60227, and the last 27 are repeated.
Okay. And that's going to be milliliters, right?
Yeah.
All right. So first of all, do we have a device in the hospitals that can measure that precisely? No. 4.6. Right? Or, okay, and if you look at this, okay, this has 3 sig figs, so maybe 3 digits, right? So 4.60 is a good way to know how to round. Because this was your only known measurement. These are conversion factors, so we don't base it off of those. Does that make sense? And again, it's going to be multiple choice. And I'm not going to say, here's the answers. Which one is it? I'm not going to do that, okay? I only say that because that's happened to me before in a class. I think, oh my gosh, that is so dumb. No, I won't do that. Anything else? So that was, let's see, dimensional analysis. Then we got atomic theory, subatomic particles we did last time. Atomic isotope symbols. So X, A, Z, and C. You understand those? Okay. Study those a few times, 10 times before you go into the exam. So you can know how to calculate the number of protons, neutrons, electrons. Yeah.
Can you go over subatomic particles one more time?
So just the properties of them. Okay. You got protons, neutrons, and electrons. So protons have, so the relative mass, 1, 1, and 0, right? Relative charge is +1, 0, and -1. And then where they're located, nucleus, and outside nucleus. Yeah? And then the attributes, proton is the atomic number, right? Determines the element. Neutrons determine the mass, or the mass number, which is protons plus neutrons, right? And the isotope. What isotope we have. So we talked about silver 107 and silver 109. That 107, 109, that's the mass number, but it's determined by the number of neutrons. Okay. And then electrons determine properties. Talked about the valence electrons, right, today? And the charge. Because that's the only part that changes in a chemical reaction, or the number of electrons. They'll either come off or go on. Good? And we'll talk more about that next unit. Exactly what happens. Okay. Anything else?
Are you giving us another conversion?
What?
Are you giving us conversion?
I like conversion factors or conversion problems?
Like 1 foot equals.
Yeah, I will give
You're
you,
providing those?
I will provide anything that's not metric to metric.
Okay.
So those prefixes you have to know. Yep, so if you don't know them by the time the test happens, you better write them on your reference card.
Okay.
Good? So did we already make our reference sheet, reference card? Let's get that going. In fact, what I would do next unit is start writing that as you go and practice using it. That way it's more useful to you. Because if we get done and I get the same results from this class as I did last semester I taught, then I'll say, okay, it doesn't do anything. We'll just say no card. I mean, I'm going to let you have a card this semester, but oh, good, that's all I care about. Okay, yeah,
You
that's,
said it was a 3x5?
yeah. So one of the smaller ones, not the postcard. Okay. Yeah, yep. You want to hold it up high so everybody can see? Oh, nice modeling. Anything else? Well, we still have 20 minutes. You guys can't go yet. No, I'm just kidding. No, really, if you have, and then the periodic table stuff we did today, the different classes, the different groups. Oh, should we go throw that sodium in water since we have time? And you guys can take your stuff out there and just leave when we're done? Oh, I hope I have it in here.
Do you just carry sodium?
Yeah, don't you? Oh, let's see if I do. Oh, yeah, here it is. No, I put it in here on purpose, just for this. And here's the funny thing, I bought this from Amazon, because it was cheaper there. And it came in this Disney cartridge. I'll take it. All right, I didn't bring any safety goggles, so we're gonna have to make sure and be far apart, far away from it, okay? I'm gonna lock this door, because I'm gonna just leave my stuff in here, so make sure you grab all your stuff. And let's see. Anybody see a container in here that's... Oh, heck yeah, is that... Oh. That would be better. Free chips. Anybody want some Pringles? No, throw them out, no one, you don't want them? Oh, heck yeah. I don't have these little ones.
So are we doing this out the hall or?
Should we? No, let's do it outside.
Outside.
Let's do it on the, where are you guys going, the north side or the south side? I don't know what that way is. South? Oh, the east side? Okay, let's go out the south doors. So, I'm gonna go down the elevator if, oh yeah, guys, we need your laptop next time.
No, I've had to.
Laptop or tablet? Yeah, that's fine. No, if you need a laptop, go to the, library and see if you can check them out, but get there sooner rather than later. So check with them maybe today or tomorrow or sometime, right? But yeah, you need a laptop for this, not a phone. Okay. Anybody want these chips? I'm gonna throw one in. Yeah, same class. No, I'll need a tablet. Yeah. iPhone.
Okay, thank you.
Yeah.
but I will study the hell out of this. And next semester, they'll be like, "You're a genius. You should not even have to take this class." So it should be a 1 terabyte. I don't know how big or small or anything. Any of that stuff is. I'm not a computer person, or else I would, have a great job and not have to worry about it.
Overkill, but yeah, you'll be good.
So, like, I don't need you to do anything right now. I know there's another class coming in and everything, so you can have the weekend. I'll come back Tuesday, or
No,
I can be patient.
I have it right here, I'll just get it to you.
Awesome.
I was hoping you didn't decide not to.
Oh, no,
Okay.
no, my mom fell and she
No.
cut her head open.
Oh, dang it.
So I had to take her to the hospital and all this stuff, and she's talking a lot of gibberish, so they set her up for an MRI and like just all this,
Dang, yeah, I'm sorry.
just one thing
That
after another,
sucks.
so. But I appreciate you waiting for me, not giving up on me. You even remembered my name. That's a lot.
That's because you came to me. I mean, that's a lot easier when a student comes to me.
Yeah.
A lot
Instead of
easier for me to
all-
remember the
yeah.
name.
Instead of like 50 of them, like.
But some
yeah,
of them come in
totally.
late, I never get their names. Like, sorry,
yeah?
I don't have time to get to know you because you just sit in the back and I just, okay, what's their name? And that's
Yeah.
all you think about.
Take out the
What's
face,
their name?
Yeah, I don't know. I tell everybody I have 2 kids. I gave them their names, so I don't even know their names. So I'm the worst with names. Your face, I'll know you 10 years from now, but
Yeah.
name, no, not so much. And I am the most technology illiterate person there is. So, if you don't mind my complete stupidity, I'd like you to show me Canvas,
Okay.
like how to print. Because I want to print everything out before I drop anything and lose everything,
Yeah.
everything and anything. I wish I was technology. I wish I had any kind of technology
All of the stuff I'm giving you is
Yes.
everything that's on
that's on there.
Canvas.
Okay, so I
So
can
you
just print from
don't
there.
even need to.
Oh, sweet. Okay, awesome. Awesome. So I work for Fox, Channel 13.
Uh-huh.
And when they interviewed me, the head guy at the time, he goes, how are you with computers? How are you with this? I go, I'm not good at all. Anything that could go wrong will go wrong on my shift. And he still gave me the job, so
Huh.
lucky for me, nothing went wrong.
Because you're honest, huh? Let's see. Okay, that one's yours, right?
Yes. Unless all the answers are on that one, then no, that one's mine.
I'm gonna give whatever's on here.
Yeah, there was one girl the very first day. She just was sitting over there. It's the first and only time they saw her. It came like another time or 2, but she wasn't in here at all. So I was dropped the
What?
class, or I don't know. 'Cause I didn't get the name. I saw her one
Yeah.
time, only one time, and was
Huh.
here any time after that. But not that I've been here
Yeah.
a lot, once or twice. Yeah,
Yeah.
once or twice more, but.
So here's how I have it set up here. So here's your Chem 1110 materials, Exam 1 material. So you have, this is like the notes.
Mhm.
Here's the Exam 1 study guide. Here's all the links to like all the videos and stuff.
Okay.
And the guy that I made this for last time, he said that some of the links were off, but they're, so
That's okay.
And then if you go into this practice, there's all the worksheets with the keys
Sweet.
for
Okay.
for that Exam 1.
Yes.
And so here it says, okay, here's the mastery, say intro to science, chemistry, intro to matter. I think this is the videos of the lectures.
Mhm.
They're not mine, but
Okay,
Um,
as long as the point gets across, right?
and then, well, if you get it one way and then get it from me a different way, I think that might be
Yeah,
actually better,
yeah,
so.
yeah.
And here's the homework, going through the homework, and that is that same professor going through the homework.
Okay,
And so that's how each one is gonna be set up, kinda like that.
okay, sweet. Yay, you're my favoriteest ever. Woohoo! And it like blows my mind. I took a picture of you on the very first day,
Uh-huh.
and I'm like, you look exactly like my cousin, exactly
Oh,
like
yeah?
my cousin. It's like it blows my mind, and
Doppelganger.
it kind of a little bit sounds like him too. Like, I thought he lived in Arizona, but here you are. But yeah, thank you so much. I
Cool.
appreciate it.
Yeah, you bet.
See you next semester,
All right.
hopefully. Yeah, you had like the highest stuff on the rate my professor stuff, so.
Well, cool. I don't even know how to check that stuff, so.
That's what a lot of them say, I'm like, I don't know why, because most of them get very good. Yeah, but that's okay. Thank you so much.
Okay, thanks, Sarah. Good luck. Good luck with your mom.
Can I have one of these?
Yeah.
Periodic table?
Periodic table.
Is that
And
okay?
sorry I printed it bad, but,
That's okay.
and then that other side is so that's what you get on every exam.
Okay. Sweet. Okay, thank you.
Okay, thanks. Take care. You're gonna have to remind me your name again.
Damaris.
Damaris. I'm gonna get it. And Krita and Hannah, right?
Yeah.
Okay. Good, good, good. Well, Andrew, Albert, how you doing? Good, and you?
Pretty okay.
Alex, see you.